Okay, let's get this done and see if we can have some time to hang out at the end. This is second period. It's freezing. Is it cold in here?
I'm so cold.
Like it is like.
It is not that cold.
It's cold in here. Like I think it's cold in here.
Hey, you're wearing a coat.
No, I'm not.
I mean, you're surrounded by a coat.
It's back there.
Huh?
It's just like padding for the seat.
Okay,
Actually
fine.
really comfortable.
All right, so this lab we're going to do on Thursday. And now we're going to talk about what's called coupling. It's called coupling. So, a reaction with a positive delta G. So, let's first of all remember, what does a delta G mean? Delta G is spontaneity, right? If you are positive, does that mean that you will happen or not?
What?
A positive delta G, is that favored or not favored?
Probably not favored.
Right. Positive delta G means it's not spontaneous. Can be forced to occur by applying, that shouldn't be a blank, just energy, just by applying energy. So there's three main ways we can do that. Number one, using electricity. So we could use electricity in the process of electrolysis to charge a battery. So if your battery runs out on your phone, your battery is not going to spontaneously charge on its own, right? That would be awesome, but it doesn't. We watched the new Annie, which isn't new, but we hadn't seen it. The new version of Annie from like 2014. Yeah, it's really good.
Yeah.
My daughters loved it. So we watched that over the weekend. That was good. I was thinking about that because like Stax, the guy has like the phone company, Jamie Foxx. Yeah. Anyways, you could use also light, because light has energy, to overcome a highly endothermic ionization energy, or light-initiated photosynthesis. Light-initiated photosynthesis in the equation below that has a delta G of positive 2,880. So this equation is actually super unspontaneous. So this equation right here, we usually write light above the arrow. This is basically the preface of like all life, right? Carbon dioxide plus water yields sugar and oxygen. Without light, this would never happen. Without light, that would never happen. So it's kind of interesting to see that photosynthesis is not a spontaneous reaction. It needs, yes. All right, flip it. So what we do is called the coupling. The coupling of a thermodynamically unfavorable reaction with a positive delta G to a favorable one with a negative delta G, where intermediates, so we're talking about intermediates again, are common throughout a series of reactions, and taken together, the reactions combine to form an overall reaction with a favorable negative delta G. So I've given an example here. So an example would be, an important cellular reaction in biochem is the addition of phosphate to a glucose molecule. What are we making here? ATP, yeah, you got it. So PO4, 3 minus plus glucose yields glucose 6-phosphate. This reaction has a positive delta G of plus 13.8 kilojoules per mole. Now, notice that's not like a huge amount to overcome, right? So this reaction has a positive delta G value, so it's not thermodynamically favored. It's not thermodynamically favored. Another important reaction of cells, and once again, I hate biology, is converting ATP to ADP in the body. But like, it's still kind of important. And I actually still like know my biology a little bit. Anyways, I don't know why I was just bragging, but I did. So anyways, ATP is in equilibrium with ADP plus PO4 3 minus. So this reaction number 2, has a delta G of negative 30.5 kilojoules per mole. Do you guys see it? Yes? So This reaction has a negative delta G, so it is thermodynamically favored. This means that a cell can convert ATP to ADP in reaction 2, and then can use the PO4 3 minus made to cause the thermodynamically unfavored positive. I want to make sure I'm actually recording. I am. This period. Reaction number 1 to occur. As long as the negative delta G reaction for number 2 exceeds the positive delta G from reaction 1. So it has to be greater, right? So this was positive 13. So this had to be at least negative 13.9, right? Okay. Then the overall reaction combo of the two will be thermodynamically favored. So here would be the combination of the two. So if I combine them together, I would have ATP plus glucose is in equilibrium with the glucose 6-phosphate, Mr. Worth would love this, plus ADP. And my delta G for this reaction would be positive 13.8 plus negative 30.5 for a total of negative 16.7 kilojoules per mole. I feel like I'm off the screen. So where did my other stuff go?
The phosphate is just an intermediate. So
Exactly. The phosphate is an intermediate.
Wait, delta G was what?
Negative 16.7 kilojoules per mole, because the positive plus the negative, you're just adding them together.
So delta G equals. Oh, so it's like 13.8 minus 30.9.
Yeah.
Oh, okay.
I just did it as a positive, as a plus, a negative. You got it. So this process of combining non-thermodynamically favored and thermodynamically favored reactions to produce an overall thermodynamically favored reaction is called coupling. Get it? You're coupling. You're putting two things together. Okay. The relationship between delta G and K. So here comes back equilibrium. So we are talking about K as in the equilibrium constant here. So consider the mathematical relationship between delta G and K that we're about to write. Here's the equation. Delta G at standard conditions is equal to negative R times T times the natural log of K.
why are there so many natural?
Well, I don't know, in all honesty. For some reason, chemists just love having natural logs and logs in here as
What
much.
is a natural log?
Natural log, that's like the opposite of E. It's just a mathematical function in your calculator. It's something that on something like this, they're going to give you everything but one. It's going to be a plug and chug. Because R is a constant, right?
Oh, that's ideal gas.
So this is back to the second R. So not the ideal gas constant, it's the second R, the 8.31451. T's temperature Kelvin, and then you're either going to know K or delta G. So K can have a huge range of magnitudes, from very tiny, from numbers like 10 to the negative 40th,
That exists.
yes, to very massive.
Does 10 to the negative 40th happen at all? Like, is there?
I mean, it's happening, it's not zero, right?
Yeah.
It's not zero. Massive numbers like 10 to the 120th.
Okay. Well, that's just a forward reaction.
So that's a large range. But remember, K is always what? Have you ever seen a negative K?
No.
There's no such thing, right? K is always positive. Delta G has a range of magnitudes that tends to be more narrow, a little more narrow than K. But delta G can be positive or negative. So let's look at three scenarios. If I have a large magnitude negative values for G, so that means that it's what? It's spontaneous, right?
Yeah.
So what type of magnitude would that lead me for K?
Is that a
That-
large, like large negative values of delta G?
Large magnitude of negative values. This would lead to a large magnitude much greater than 1 values for K, right?
Oh, right, because
Oh.
negative G wants to react.
Lots of products.
K is products over reactants. You got it. Larger values of K mean reactions are thermodynamically favored. They're thermodynamically favored with many products compared to reactants at equilibrium. Compared to reactants at equilibrium. Exactly. That's what we were talking about. Large magnitude positive values for delta G will lead to small magnitude, much less than 1 values of K. So small values of K show that reactions are thermodynamically unfavored. Unfavored with many reactants compared to products. Which makes sense because we know that K is products over reactants at equilibrium. When the value of delta G is close to 0, i.e. not very positive or negative, that's going to lead to values of K that are close to what? 1. Such values of K show the reactions are close to having reactions and products equally favored, aka what? Equilibrium. Aka equilibrium. Flip the page.
Wait, so if K is 1, then it would be a
Correct. Because Q and K would be equal to each other, right? So remember, queen is less than king, that's right. Queen is greater than king, that's left. Okay. Remember, delta G assumes standard conditions of the following: 1 atm for gases and 1 molar for solutions. This means that when conditions differ from those standard values that are previously positive or negative, delta G value will take on a new delta G value under these new conditions.
Is that like changing the temperature and changing?
It's like you're almost shifting it, right? Not technically, but like it's going to change it. It's going to change it. It is, because if delta G and K are related, right, in that equation, if you change K, you're going to change your delta G. If delta G was close to 0, it could actually cause a non-favored. It could actually cause a non-favored reaction to become a favored reaction. So, in college, I just wanted to throw this out there. You will not see this on the AP test. You may see an equation like this. It would be delta G is equal to delta G standard plus R times T times the natural log of Q. So this is looking at the initial conditions before we even reach equilibrium. This is not the AP test. You should be able to qualitatively explain this paragraph though, right? This paragraph makes sense, what we just said. So we were just saying that if my conditions change, that changes K, which is going to change G. Okay, so this is kind of our last new topic. Yahtzee, and this is actually fairly easy, so that's good too. Electrochemistry.
Oh, just did some physics.
Electrochemistry.
We just did electros.
So, do you guys remember redox? It's all going to come back now.
Is this like
Oh, crap.
This is half reactions.
Let's go.
We skipped half reactions way back. We're talking about redox. We've saved it till now. So here we go. Let's first talk about electrode potentials and half cells. When a metal is placed in a solution containing its own ions, a reversible reaction is set up. So here's my metal M. Here's my metal M. Metals have what type of charge? I'm just going to put X positive. X is any number.
Right.
Because metals want to do what with electrons?
Lose electrons.
Lose. That's AQ. Plus X number of electrons
This is one.
is in equilibrium with the metal in its solid version. Because metals like to give away electrons. Reactive metals such as magnesium lose electrons readily. And the reaction lies relatively to the, which way?
Right.
To the left. Because I'm giving up electrons on the left side. So I have Mg plus 2 electrons that I'm giving away is in equilibrium with Mg solid. Less reactive metals such as silver show less tendency to lose electrons, and the reaction lies relatively to the
Right.
right. Relatively to the right. So if I have Ag, which is a +1, plus it giving up that electron, that's in equilibrium with Ag solid. You can also look at nonmetals. For example, this is weird. Hydrogen, right, has a positive charge, Aq, plus an electron.
Why would that?
Hydrogen wants to,
Why is the hydrogen ions aqueous and the metal ions aren't?
these were also aqueous, I just didn't draw it. Also aqueous. What would that be in equilibrium with? This is tricky.
Is it water?
There's no oxygen in this equation.
Okay.
Hydrogen is diatomic,
Okay.
but that we can't just like create hydrogen, can we? Like it needs to be H2.
It needs to be
So it
H2,
needs
but how would I balance that?
Make it B2 of hydrogen.
No, because we need more electrons.
No,
Ha, 0.5.
1/2.
Ain't no way.
1/2 H2 as a gas. Yes. So you can have half moles. You can have half moles. So whenever an element is placed in contact with a solution containing its own ions, an electric charge will develop on the metal. Or in the case of a nonmetal, on the inert conductor placed in the solution. So there's got to be some other conductor in there. The charge is called the electrode potential. It's called the electrode potential. If you've been doing this in physics, this is exactly the same thing. And the whole system is called a half cell, because there's two halves to each part of this cell. The sign and the size of the charge will depend on the relative ability of the element to lose or gain electrons when compared to the hydrogen half cell. So this is, don't flip it yet. So this is all based off of hydrogen, okay? So every single reduction potential is based off of hydrogen. So I'm going to write that one more time. So I have hydrogen, which is positive, plus 1 electron. That is, once again, in equilibrium with 1/2 of H2. Okay, what was your question, Megan?
Why
Okay,
can't you just double the length?
because I don't want to have, I only want one hydrogen ion.
No, so
A
you
hydrogen?
have one.
Correct, I only have one.
That's crazy.
I only have one hydrogen ion. Now we can flip it. Flip the page. This room is like warm in the fall and cold in the winter. I don't know why.
Warm in the fall is cold. Maybe it's
Well, I think it's
colder
because
in
that crack in the wall over there leaks cold air.
Probably
in.
because it's colder in the winter than it is in the fall.
In order to make meaningful comparisons, I'm saying very technical things, Jaway, okay?
What?
No, I think the air conditioning and the heat just doesn't work very well in this room.
yeah.
So it's like the extremes.
In the whole school, like,
Yeah. Some rooms are like extreme though.
yeah.
Like this room isn't like super hot or like, I forget it's kind of cold. But like some rooms, like up in the history like wing, those can get like freezing or like really hot. It's also upstairs. So, all right. In order to make meaningful comparisons, it's necessary to stipulate a set of standard conditions. So once again, standard conditions are important. Standard conditions under which the electrode potential of a given half cell is measured. The standard electrode reduction potential of a half cell, or also known as E, or sometimes you'll see it as SERP,
How do you spell that?
SERP, because it's the standard electrode reduction potential,
Oh, cool.
right, is defined as the electrode potential of a half cell and measured relative to a standard hydrogen electrode, which has a value of 0 volts That does not say OV. That says 0 volts under standard conditions of, once again, 298 Kelvin and gases with a pressure of 1.0 atmosphere and solutions with a concentration of 1.0 molar. So here is the setup of how this would be done. So we have hydrogen gas at 1 atm, and in order to make this happen, we have to put something that conducts. So we put plutonium. So plutonium metal is a wire inside of the glass, and inside of here, I have my aqueous hydrogen ions at 298 Kelvin. The most important part of every chemical cell is the salt bridge. So put a circle around the salt bridge. The salt bridge helps there not become an overload of one type of ion on one side. Because if I get too many positive, it won't run. If I get too many negative, it won't run. I think it was 4 years ago now, on an FRQ, they drew a half cell. And all the question was, will this half cell work and why?
Did it not have a,
The answer was no,
did it not have sulfur?
didn't have a salt bridge. That was the only thing wrong with it.
The 2014 FRQs had one of these problems.
Yeah. So these are actually really easy to do, and we're gonna, as we work through them, like it's super easy. But salt bridge is super important. So the practical use of the hydrogen half cell for determining E is the following. Number one, it's time consuming. It's also difficult to set up because plutonium is what?
Gonna kill you?
It's radioactive.
Yeah.
Number two, it's fragile and non-portable. It's really hard to do. So because of this, all electrode potentials are in your book, and also some of them are on this page, the way it copied, not on the next page. So notice, put a box around this, these are reduction potentials. So you will be given whatever value you'll need on the AP test. So these are all based off of hydrogen, and because of that, we know all of these reduction potentials.
This has to be plutonium that we use for like the metal.
For hydrogen, it's plutonium. It doesn't always have to be.
Wait, for last
If you're dealing with like magnesium, you're going to have magnesium metal.
Yeah, yeah.
For
Or
last
copper, copper.
For last chapter, did we have AP classical questions?
No. Because there was multiple choice on the test,
Oh, yeah. Oh, right, yeah.
which you guys did well. So nice work. You guys saw that I put them in, right?
Yes.
Okay, good.
Oh, yeah.
Okay. So species that appear at the top of the series gain electrons more readily. So once again, oil rig, oxidation is losing, reduction is gaining. So, I know. Therefore, those have the most positive E values and are easily reduced, which means those are the best oxidizing agents. So things with the greater delta E like to gain electrons, which means they're the most easily reduced. That's important to know, first of all. Second of all, species that appear at the bottom of the series lose electrons more readily and therefore have the most negative delta E values and are easily oxidized, which makes them the best reducing agents. So this chart is going to be super, super important. We're going to use either this chart or there's something similar to this in our book. So this chart is really, really important. Flip the page. So what do we do with this? What we do is we make galvanic or voltaic cells, also known as batteries. Do you guys ever see the video of like them putting like a piece of metal in a lemon and it lights up the little light bulb? That's what these are. Because lemons have acid. You got it. It's just chemistry. So a galvanic cell is the apparatus for generating electrical chemical energy from a spontaneous redox reaction. Notice that it said spontaneous for galvanic. Okay, that's important for galvanic. Connecting two half cells that have different electrode potentials. Why do they have to be different? If they had the same electrode potential, would there be any difference? Would there be any flow of electrons? No. You got it. Forms an electrochemical battery cell, also known as a battery. A salt bridge, so I'm going to put that once again in all caps, because you never want to forget the salt bridge, connects the two half cells. A salt bridge can be made with something simple, like a piece of filter paper. There just has to be something that can help soaked in a suitable ionic solution, like potassium chloride or potassium nitrate. Why do I want it to be ionic? Because an ionic compound has a positive and also a negative side. You got it. The solution used in the salt bridge must not interact or interfere or react with the two half cells. For example, potassium chloride couldn't be used if one of the half cells contained silver, because that would react with the chlorine ions, causing a what? Precipitate. You got it. Nice work. Causing a precipitate to form, causing the concentration of the ions in the solution to decrease. You don't want that. The salt bridge is supposed to be allowing for the transfer of ions, not electrons. We're talking about ions between the two solutions. Which completes the circuit. Ions will flow in order to balance the charge. For example, here's a zinc and a copper cell. So here's my zinc electrode. Notice that it's in Zn plus 2, aqueous ions. Here's my copper electrode. It's in Cu2 plus ions, because it has to be in something similar. The electrons will flow through the wire toward the most positive half cell. So in this case, how would it flow? So we would have to go back here and look at our reactions. So what is more positive, Zn plus 2 or copper plus 2? So I'm looking here. I have copper plus 2 is a plus 0.34. You guys see that? And zinc is negative 0.76, right? So in this case, it's going to be flowing from zinc to copper. As a result, the copper ions gain electrons. Sorry about that. Copper ions gain electrons and are reduced. So we could draw an arrow here. This is moving, the ions are moving this way, from left to right. Moving left to right. Whenever I draw cells, I draw them that they're moving left to right. It doesn't matter how you draw them, but here's why. There's a short form, or a cell diagram can be written like this. So the short form for this would be zinc, which is my metal, right? Slash Zn plus 2. That's one side of my half cell. So I put a double railroad there. Is flowing to the copper 2 plus slash copper. If you would be given this short form, you could literally draw a whole cell from that short form. So this is saying that zinc is being what? Oxidized, and copper is being reduced. That's what this is saying. So more on that short form diagram. The reduced species is placed on the right-hand side. This is the cathode. That's the cathode.
Oh, this is cathode and anode.
The oxidized, you got it, species is placed on the left-hand side. That is the anode. So the vertical line, so I do it as a slash, represents the different phases. So the single line represents the different phases present in each electrode. So here's my solid, here's my aqueous. in the two electrodes. The double vertical line represents the salt bridge. So here's my salt bridge connected to two electrodes. Different species in the same phase would be separated by a comma. So you could see something like this. Fe 2 plus, comma, Fe 3 plus. I don't think you'd see that on the AP test, but it's possible. The presence of an inert conductor, if there's no solid metal present, so like for hydrogen, could also be shown inside of parentheses. For example, well, see, I'm always getting ahead of myself. The hydrogen half cell, it would look like this. Parentheses, plutonium, slash 1/2 H2 slash H plus. That's a really weird one.
I hope I never see it.
I don't think you will. Or if it's reduced, it would be the opposite, right? So it would be H plus slash 1/2 H2 slash my plutonium. I have never seen that on the AP test. I've never seen this on the AP test, but it's just something good to know. And that's what I wanted to get to today. So let's call it there.